welcome you all in NPTEL online certification course on mechatronics. Today we are going to discuss about electric circuits and components. Electric circuit and components, they are very vital part of any mechatronic system, as the mechatronic system consists of many electrical components and their connections. So, today we are going to see some basics about electric circuits and components, which are useful from the mechatronics perspective. Electric circuit and components, as I said, they are important in design of discrete circuit for signal conditioning and interfacing purpose. So, as we have seen the basic block diagram for any mechatronic system, we have actuator, sensors, and then we have the signal conditioning and interfacing unit. Okay. So, this study is very important from that perspective. Now, we all know from our basic knowledge of physics that electron moves and produce electric current, and useful job can be done by these energized electrons. And why does the electron move? The electron moves because we impose an electric field, and that electric field imparts energy by doing work on the electrons. A measure of this electric field potential is the voltage, as we know, and this voltage is also referred to as electromotive force, or in short we write as EMF. Current, as we know that it is a time rate of flow of charge. Okay. So, the current which is function of time, this is actually given by dq by dt, where q are the charges. Now, we come across the two types of circuits, that is the DC circuit, direct current circuit, and alternative current circuit, AC circuits. So, DC circuits are the circuit where voltage and current in a circuit are constant, that is they are independent of time. Whereas, in case of AC circuits, voltage and currents vary with time, usually in a sinusoidal way. So, if we look at this figure, basically this figure depicts the electric circuit, and here you can see that in this figure we have a voltage source and there is a load, and this is the direction of the flow of electron flow through the conductor, and the conventional way of the current flow is taken opposite to the sense of the electron flow. So, we have this direction as the current flow direction, and there is a voltage drop across the load. So, this is how an electric circuit looks like. There could be alternate way of representing these circuits. Here say we have a source and we have a load here, and one end is grounded here. So, or it could be represented in this way, where rather than the separate ground, we have a common ground. Now, as I said, these voltage sources add energy to the electrons, and at anode electrons are attracted and at cathode electrons are released. These are all basic preliminaries which you study in case of cells also. Okay. So, we will be just going through these. Now, electron flow from cathode to anode through the circuit, but standard convention, as I said, it is in the opposite direction, and load basically consists of network network of circuit element that may either store in energy or that may dissipate energy. So, there are two energy storing elements which we call as the inductor and capacitor, and the dissipative element is basically resistor in case of electrical circuit. Okay. And the ground indicates a reference point in a circuit where voltage is assumed to be 0. So, it is basically a reference. Now, coming to the basic electrical elements, as I said, our purpose of this lecture is to study the elements which we come across in a mechatronic system. Okay. So, the basic elements are the passive elements or passive components and active components. So, as the name indicates that in passive component these components do not require additional source of power basically. So, these components are resistance, inductance and capacitance. And if you come to the active components, these are the components which require additional source of power, and these could be either the tube type of devices which were used earlier in the electronic circuits, or they could be the solid state devices which are basically the semiconductor devices. Okay. So, in tube type devices we have the vacuum tube and say gas tube, and in solid state devices we have diodes, transistors and so on. Okay. So, this is the basic classification of the electric elements. As I said, the passive elements we have resistor, capacitor. Here there are two notations of the capacitor, they can be represented either way, and the inductor. Resistor is a energy dissipating element, whereas the capacitor and inductor are the energy storing element. And then there are the two sources, the voltage source and the current source. So, these are the representation of the two sources. Current source, you can see that inside a circle we represent an arrow and that basically tells us the direction of flow of current. So, as I said, passive electrical elements are resistor, inductor and capacitor. Resistance is indicated by R, inductance is indicated by L and the capacitance is indicated by C. And as I said, passive elements require no additional power supply, unlike active elements such as integrated circuits. I have talked about diode and the transistor also as the active elements. Okay. These elements are defined mathematically by the voltage current relationship. Okay. And as I said, there are two types of energy sources, that is the voltage source and current source, and the ideal sources we assume that although there are no ideal source, but to simplify our analysis we assume that the ideal sources contains no internal resistance, inductance or capacitance. So, let us begin with the first passive element, that is the resistor. Okay. So, resistor we can see that it is a dissipative element that converts electrical energy into heat, okay, and the heat is dissipated to the universe or atmosphere. Okay. And if suppose I have a wire resistance conductor of say length L and area of cross section A, and resistivity of the material if it is rho, then this resistance is defined as rho L by A. Okay. And this is the notation basically how it is represented in an electrical circuit. Do not confuse this type of notation with the spring notation which we will be talking later. Okay. And so, Ohm's law defines VI characteristic voltage and current characteristic of a resistor, and we all are very well familiar with the Ohm's law, which says that V is equal to I R. So, here is a plot which gives the voltage current relation for an ideal resistor. Okay. So, the ideal one, we can see that V is equal to I R. So, the resistance can be found out as V by I, that is the slope of this curve will be giving us the resistance. Whereas, in case of the, and you can see that this relationship is linear, whereas in case of the actual resistor, the relationship will not, real resistor, the relationship will not be linear, and after a certain amount of current or once the current value exceed a certain value, the resistor will fail. So, this is where the failure is indicated. Now, these resistors are available in the market in various form of packaging. Our aim as a mechatronics engineer to make different circuits, different components to be used in a mechatronic system. So, we need to know that what type of resistor or what is the packing which is commercially available in the market for procuring the resistor. Okay. So, it could be wire lead type. Here you can see here there are various bands. I will be talking about these bands little later. Then we have a surface mount resistor where at the ends you can see that there are solder taps, and there are dual inline packaging where you have the two lines here, as you can see two line of pins are there, and commercially they are also available in the form of single inline packaging where you can see that there is a single line. So, this way we can go and get them in the market. Coming back to the first case which I was talking to you, that is the wire lead type. Okay. So, if we look at the wire lead resistor, there are different color bands actually in it. You can see A, B, C, and then there is after a gap there is another band which we call as the tolerance band. So, here basically the resistor value with this help of color band you can measure the value of the resistor, okay, which we measure in terms of the ohms. Okay. And this value of resistor you can also measure with the help of multimeter, but if you know this color coding without help of multimeter you can see what value of resistance this resistor will be providing. Okay. So, resistor value and tolerance, these are expressed as R is equal to AB into 10 to the power C plus minus tolerance in percentage, where basically this A band indicates the 10 digit, and B band indicates the 1 digit, and C band basically indicates the power. And these values of A, B and C band are actually given based on the color code actually. Okay. So, these values are based on the color code. For example, here you can see for black there is 0 value, brown 1, red 2 and so on. Okay. Similarly, for the tolerance band, depending on the color we have the tolerance values. Okay. So, this way we can identify the resistor value. Then we also require many times the variable resistor, okay, especially in a device called potentiometer, or in short it is called as pot. We often require the variable resistor, and these variable resistor provide range of values, and these values could be controlled by say some mechanical screw, knob or some linear slide. So, if you have a linear slide and that slide is moving, the resistance value is moving. Okay. So, that type of arrangement could be there, and so here is the notation basically 10K. You can see the either it could be represented like this, the variable resistor where an arrow is touching here, or it we can arrow touching here, and here we can see that there is a symbol provided, which means that you can change this value through the screw knob, or it could be a simple this way the variable resistor can be indicated. Then next passive component is the capacitor, okay, and it is a passive elements that stores energy in the form of electric field. Okay. So, here you can see that a parallel plate capacitor has been shown over in this figure, and there are two terminals, the positive terminal, negative terminal for that, and basically there are two parallel plates, and in between the parallel plate there is a dielectric material which is a non-conducting material which is there. Okay. So, the field is the result of the separation of charges here we can see, and the dielectric material is an insulator basically that increases the capacitance as a result of permanent or induced dipole in the material. Strictly speaking, the DC current does not flow through the capacitor, and charges are displaced through the circuit, and there is a current what we call it as the displacement current, which is defined for a capacitor, and this current integration of this current basically divided by C, that gives us the voltage, or Vc is Q by T, or we can also evaluate I is equal to C dV by dt by differentiating this equation. So, we can see that capacitance is a property of the dielectric material, plate geometry and the plate separation. Okay, I am not going much details of these things, you must have studied in your 12th class all these basic concepts. My emphasis is here rather on just reviewing these concepts from the mechatronics point of view. So, the values of typical capacitor ranges from 1 picofarad to the 1000 microfarad. So, this we have to keep in mind while selecting them for our component, our mechatronic system. Next important component, mechatronic component, is the inductor. Okay. So, inductor again, as I said, it is a passive element that stores energy in the form of a magnetic field, and energy storing elements yes stores energy in the form of a magnetic field, and characteristics are from the Faraday's law of induction. So, Faraday's law of induction says that the voltage is d lambda by dt, where the lambda is the total magnetic flux through a coil winding due to the current. Okay. And this magnetic flux is proportional to the current, and if I remove that proportionality symbol with a constant, we define inductance of the material, that is L. Okay. So, we have Vt is L di by dt, or from here I can evaluate I is equal to 1 by L integral of V tau d tau, where tau is basically a dummy variable in order to integrate the voltage. Okay. And this magnetic flux is measured in terms of the Weber, and this is how you can see that the flow of current causes the magnetic field. So, the current through an inductor cannot change instantaneously because it is integral of the voltage. Okay. So, here you can see that this current is integral of the voltage. So, this cannot be changed instantaneously, and because of this we have something to say, we have something to look for for a components which have high value of inductances and which are used in the mechatronic system. Motor is one of such components. So, if your motor has got large inductances, it is difficult to start and stop motor instantaneously. Okay. And the unit for measurement of inductance is Henry, and the typical inductance range is 1 microhenry to 100 millihenry. Okay. So, these are the values. Next thing, important thing is that how do we analyze our electric circuit? As I said, we will be using these components to make our mechatronic system. Then if we want to analyze this mechatronic system, say if you want to find out the voltage across some element, or say we want to find out the current through some element, okay, then how could we do that? Okay. So, Kirchhoff's laws are very useful for this. There are two Kirchhoff's laws, Kirchhoff's voltage law, which in short is called KVL, and Kirchhoff's current law. Okay. So, we will see both of these. So, suppose I have got an electric circuit like this. Now, in this electric circuit, basically what we do is that we assume a direction of current, and whatever elements comes across in that current direction, we can have the voltage drop. So, we have a positive here, negative here, there is a drop of voltage across these elements in the direction of current, we can see over here, and we can form a loop through all these components. Okay. And then we can write the Kirchhoff's voltage law, which says that sum of the voltages across a closed loop or path is 0. Okay. So, if we have n components here, so sigma V I from 1 to n is equal to 0. Now, how do we take care of the signs here? So, we can say here we can start from one of the components. So, here you have a negative sign. So, this is my loop direction basically. So, minus V1 minus V2 plus V3, this is in the direction of the loop, there is a plus sign here, plus V3, and here you can see that there is a negative sign. So, I have minus Vn here and is equal to 0. So, this way we can write the Kirchhoff's law, Kirchhoff's voltage law, KVL. Similarly, the Kirchhoff's current law can be written as this, that is sum of the currents flowing into a closed surface or node is 0. So, suppose you have a node here and there is a current I1 in, I2 in and I3 going. So, we can take the in value as positive and outgoing value as negative, and we can write that Kirchhoff's current law. Okay. So, for this node I1 plus I2 minus I3, I am putting minus sign here because this is going out of the node, and plus sign for these two because these current are into this node. Okay. So, this is there. So, if I have to write a general expression across a surface, okay, various currents I1, I2, I3 and IN, I can just write it like this. Okay. So, this way we can analyze a circuit. Now, if we have a series resistance circuit consisting of say two resistor here, say resistor having values R1 and R2, this if we assume this direction of current here, say this is a voltage source, then voltage drop here is VR1 and VR2. So, if I write the Kirchhoff's voltage law here, then you see minus Vs plus VR1, if I take this as the loop. Okay. So, minus Vs plus Vr1 plus Vr2 is equal to 0. Now, if I substitute for these voltages Vr1 and Vr2, I can find out an equivalent resistance which will be going to be equal to R1 plus R2. That is, I will have a voltage source here, and I will have an equivalent resistance for this, which is I can say this is R equivalent and this is my voltage source. Okay. This way this is my direction of current. So, this is my positive and this is my negative. So, this way I can write. Similarly, if in this series circuit instead of resistance I have the capacitance capacitor with the capacitance C1 and C2, I can derive this C equivalent as C1 C2 by C1 plus C2, and if I have in series the two inductors, that is then I can write the equivalent of that as L1 plus L2. Similarly, I can use this concept in the voltage divider, and that is very helpful especially in mechatronic system if we have to take the power from say across a resistor. Okay. So, in this voltage divider basically these resistor could be used as the elements which divide your source voltage. Okay. So, for example, the voltage across this one R1 VR1 we can write as Vs times R1 by R1 plus R2. Okay. So, this again we can write this and similarly VR2 I can write as R2 by R1 plus R2 into Vs. Okay. So, again through Kirchhoff's law I can use that, and this basically means that I can tap a voltage from this one which is not Vs, which is a multiple of Vs or fraction of Vs. Similarly, I can take some voltage from here which is again a fraction of Vs. Similarly, we can find out the equivalent for the parallel resistance circuit. Here you are shown a parallel resistor circuit with say consisting of the two resistances R1 R2. Let these resistors are connected across a voltage source here, and let current through this circuit is I, and this current is split up in the two parts, say current through resistor 1 R1 is I1 and through R2 it is I2. Then if we apply the Kirchhoff's current law here, then we can see that I is in and I1 and I2 are out. So, I minus I1 minus I2 is equal to 0. Now, if I apply Ohm's law across R1 and R2, then I can find out the equivalent resistance for this one. So, R equivalent will be R1 R2 by R1 plus R2, and if I replace this resistor by capacitors say of capacitance C1 and C2, then C equivalent I can find out as C1 plus C2, and similarly if I replace this with inductance, then I can find out the L equivalent as L1 L2 by L1 plus L2. Now, we come across the voltage and current sources and meters in mechatronic systems. Okay. So, it is very important for us to understand some of the basics of these voltage and current sources and voltage meter and current meter. Okay. So, an ideal voltage source has 0 output resistance and it can supply infinite current. Okay. Similarly, an ideal current source has infinite output resistance and can supply infinite voltage. These are assumptions basically. Okay. And ideal voltmeter has infinite input resistance and draws no current. Okay. It draws no current, so that there is no voltage drop. Okay. And similarly, an ideal ammeter has 0 input resistance and no voltage drop across it, has 0 input resistance and no voltage drop across it. So, the real voltage source and output impedance, you can see an example of the voltage source here, commercially available power supply by HP is shown over here. So, the real voltage source is can be represented by an ideal voltage source plus a output impedance, where we consider this output impedance to be small. Similarly, the real current source, say we have a real current source over here, and with output impedance. So, this is how it can be represented by, and this R out of commercially available current source is very high, so as to minimize the current division effect. Similarly, the real ammeter with input impedance. So, we can see that the real ammeter is here, and R in of this real commercial available ammeter is small, minimizing the voltage drop VR in the circuit. Okay. So, here this resistance is small, so that there is a minimum voltage drop in this circuit. And we can define real voltmeter here, ideal voltmeter with input impedance, and this R in of commercially available voltmeter is very large. Okay. So, that is there, and these are some of the commercially available your multimeters which can be used for the various purposes, for current measurement, voltage measurement, resistance measurement, and so on. Now, to analyze the electrical circuit, there are two more theorems which help us in this analysis that we will be looking at. One is the Thevenin equivalent circuit, and another one is the Norton one. So, let us see that. So, to simplify and the analysis of complex circuit, we wish to replace the voltage source and the resistance network with an equivalent voltage and the series resistor. Okay. So, along with the equivalent voltage, we put the series resistor. So, this resistance network is basically replaced by the series resistor. So, the Thevenin theorem states that given a pair of terminal in a linear network, the network may be replaced by an ideal voltage source in series with a resistor. Okay. So, here VOC is equal to the open circuit voltage across the terminal, and RTH is the equivalent resistor resistance across the terminal when the independent voltage source are shorted and the independent current source are replaced with the open circuit. So, here we can see that here suppose I have a source and there are two resistors. I want to replace this portion with the Thevenin equivalent, okay, and here we have the rest of the circuit. So, what we do is that we replace this with a voltage source VOC and the Thevenin equivalent resistance. This VOC can be given by R2 by R1 plus R2 times Vs, and similarly RTS Thevenin can be given by R1 R2 by R1 plus R2. Okay. So, this way we can evaluate this. Coming to the Norton equivalent circuit, here the linear network is replaced by an ideal current source and the Thevenin resistance in parallel with source. Okay. So, here we can replace this. So, Norton equivalent circuit will have the ideal current source and the Thevenin resistance in parallel with the source, and here you will be having rest of the circuit. So, how this ideal current source is found? It is found by calculating the current that would flow through the terminal if they were shorted together, having removed the remaining of the load circuit. Okay. And it can be shown that the current flowing through the Thevenin produces the Thevenin voltage. So, I am not going into all those details. Next, I will just talk little about AC sinusoidal AC circuit analysis, and to this I will be just talking about the sinusoidal waveform here. Say there are the two signals here and they are replaced with some phase shift, say time shift delta t is there and the phase angle phi is there. Then here the term is the peak which we define from horizontal axis to the maximum value is defined as p, and this is defined as the time for this one, okay, time period, and there is a peak to peak voltage is there, okay, and the time shift between the signal and say reference, one of the signal could be reference signal, that is basically omega delta t, and the positive phase angle is what we call it as, it is there in the leading waveform, and negative phase angle is there in the lagging waveform, and this frequency of signal is given by 1 by time period, and this is omega by 2 pi. Okay. So, and our AC circuit analysis could consist of say a source here, then they have a resistor, inductor, capacitor. So, all these type of elements could be there. So, we can carry out the say AC circuit analysis. There is concept of impedances which has to be looked into, which I am not taking it here. Please have a look at it. In AC circuit we have the concept of impedances comes, which are analogous to the resistances in the DC circuit. So, that thing is to be taken care, and then this analysis could be carried out. Okay. So, with this I would like to give you references. Again these are the some of the common references, standard mechatronics books which you can look for further study. Okay. So, wish you good luck, and thank you for listening to this lecture. Thank you.